One last time, chapter 5. Okay, we're covering 3 different basic laws of fluid mechanics in chapter 5. Using the Reynolds transport theorem, taking the basic laws written for systems and converting those laws that we can use in engineering based on the control line, controlled surface approach. All right, we talked about continuity, we talked about momentum, so today we start energy. We'll kind of derive the correct equations to use with energy, and then maybe later today and for sure on Monday we'll do examples on energy. The last 2 homeworks that you have go through the end of chapter 5, which is the energy problems. Okay, obviously a very important equation. We got a little bit of that back in chapter 3 in Bernoulli, so we know something about energy and fluids, but this is the next step in that. We start off again, well, let's just get a show of hands in here. I know some of you have had it, some haven't. How many of you in here have had ME301 thermodynamics? Can we just do a quick count? 2, keep them up a second. 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, roughly 17 out of 34 people. That's about a half, okay? I understand that. You really get a good dose of that in ME301. You get a really good derivation. So for some people, it's going to be totally new in this class, and for some people, it'll be maybe a review of that. We're not going to go through as much in detail of this derivation as we do in thermal. As we see, half the class have been through this thing one time. So we're going to do maybe what you call a more casual derivation of this, not mathematically rigorous, okay? Now, we start out with the energy equation written in system terms. This is what you get in physics in ME301. Okay, this is the equation written in terms of a system, where the rate of change of the energy in the system is equal to, we have to shift gears temporarily for about 2 class periods. This Q dot now stands for heat transfer, no longer volumetric flow rate. So it's not Q volumetric flow rate, so you got to kind of shift gears. W is work, so Q is heat transfer, W is work. The dot above them means with respect to time. W is work. Work is Newton meters. Divide it by time, seconds. Newton meters per second. What's a Newton meter? A joule. What's a joule per second? A watt. Okay, it's watts. If it's British gravitational, the work, pound foot of work, pound feet of work. Divided by time, seconds. Foot-pounds per second. That's power. You can convert that into horsepower. Divide by 550. Divide by 550. Get it in horsepower if you're in British gravitation. If you're in SI, what do we say? Joules per second. What's that? Watts. Okay. So those are power terms. W all by itself stands for work. W dot is the rate at which work is done, and that's power. Okay, the left-hand side looks something, that should be, looks something like the left-hand side of our previous Reynolds transport theorem. Okay, so here they are right here. So we're going to use the Reynolds transport theorem now. So this right-hand side here equals this right-hand side here. Since the left-hand sides are the same, system, E stands for energy. E stands for energy. What's energy? Joules. Okay. Foot-pounds. Okay. So now we equate the right-hand side of the top equation to the right-hand side of the bottom equation. Okay, we do that, and we end up with this equation. Okay, so we have the left-hand side. So again, the system equation says the time rate of change of energy of a system is equal to how much heat transfer occurs, and net in means in minus out. The net heat transfer in plus the net work out. Okay, oops, that should be in, sorry about that. We're going to define that as being positive. Some books call it negative, we'll call that positive. Okay, now, remember what we did when we had continuity? This was written originally, Reynolds Transport Theorem, with a capital B. Capital B was here, capital B was here, capital B was here. We said let B equal mass. Little b was big B divided by mass. So when we did continuity, that became 1. Mass divided by mass was 1. When we had momentum, that was mass times velocity, big B. Divide that by mass. That was just the velocity. When we have energy, capital E is the energy. If we take and divide E by M, we get little e. So that's energy per mass. So little e shouldn't be energy per mass, but we know it is. Okay. And what's rho dV? That's the mass. That's the mass. Energy per mass times the mass gives me what? Energy with respect to time gives me what? The rate of change of energy in the system with respect to time down here. And over here is control volume. Okay, now let's go ahead and look at what kind of, in thermal they talk about work for about a week and describe different kinds of work. I'll just give you a little flavor of what kind of work we're talking about here. One thing, work could be a rotating shaft. How do you drive a pump with a motor? How are they connected? By a shaft. What does a shaft do? It rotates and it powers the pump to pump, for instance, water. So one way work can cross the boundaries of the control surface is by a rotating shaft crossing the boundaries. A turbine or a pump, those are examples of that. There's other kinds of work, pressure work. It requires work to push mass into the control volume, through the control surface. It requires work. The pressure work pushes the fluid, let's say, into the pump. That's going into the pump. There might be friction work. Where you have friction, let's say, on a conveyor belt with the fluid. There's friction between the belt and the fluid. So frictional work, those are all examples of what this term here might be. Okay, now what kind of energy can there be? We'll consider several. We'll start off with what's called internal energy. We'll add P over rho, energy to the pressure, plus V squared over 2 and GZ. Kinetic energy, potential energy, energy due to pressure, and this guy U, little u, is called internal energy. Pretty much it's everything you can't see. if you heat a cup of coffee up by 30 degrees Fahrenheit, it doesn't start to go red, at least it shouldn't, okay? But do you think it has more energy? Oh yeah. Why? Because the molecules are moving faster in there. Oh yeah. It's invisible, it's microscopic, I can't see it. Now, if I throw a baseball, oh, you better believe I'll see this guy right here, kinetic energy. I drop a brick from a building, you better believe I'll see this guy here, potential energy, but I don't see the internal energy. That's why it's called that. It happens internally. Okay, so that's what this guy in this equation is. We're gonna sub that in now where we see little e. So using this gives the following. ddt and now we sub in little e. And now we do what it says up here. That's E, and we have rho, and we have our V dot N dA. And then that has to be equal to, it goes way out here, Q net in plus W dot net in.
Professor?
Yeah.
Is there G net under V squared over?
Let's see, under the let's check and see. What's the units of V squared?
Meters.
What's the units of G? What's the units of Z? No, they're the same.
Gotcha.
That's the way you do it. Always just check it that way. Okay, now, in chapter 5, he pretty much tells you. Yeah. I'm sorry. Yeah.
There's another G.
Yeah.
Oh, there's another G here? Oh, yeah, I got too many G's. Thank you very much. Bernoulli came back to my mind. Chapter 5 says, in our book, in pretty much a first introductory fluids course, we normally are going to consider this guy to be 0. So normally we consider steady state, except sometimes in continuity we consider a tank increasing in mass by water going in and nothing coming out. But generally in chapter 5, we look at steady state. So we're going to assume now, to make matters simple to start here. So assume steady state. We're also going to assume incompressible. We're also going to assume inviscid or frictionless. So we're not going to worry about this frictional work for right now. We are going to worry about the work done by the pressure forces and the work done by rotating shafts. Okay, so we have all that in there, and then, so doing that, we get, now this guy's going to go out. Okay. And we're also going to assume one more. For right now, we're going to assume no net work in. We'll come back later and put that in there, but for right now, assume it's going to 0. So we end up with this m dot. Now, the m dot comes from the rho AV. This is m dot right here. Rho AV, m dot. Okay. So we pull that outside m dot. Rearrange the terms. rearrange it one more time. We just separate the terms, put some on the left-hand side of the equation, some on the right-hand side of the equation. And let's put up here, we have Q net in, Q dot net in divided by M dot. So, I think that's how we got that.
Professor,
Mhm.
quick question.
Yeah.
What happened to GZ in the first equation?
I'm sorry, which one now? This one?
Right there, yeah.
That one? Oh, let's see that. Was there a GZ in there? I've got my U's, my P's, my V's. I got my no G's in there. Thank you. I need my Z's in there. The elevation can change. Thanks so much. So we got our plus Z out minus Z in. And that whole thing is equal to Q dot net in. Okay, thanks. I think we're okay down here. Okay, we're getting there, we're getting there. Now, we say, you know what, that thing looks a little bit like the end of chapter 3, something called Bernoulli equation. It looks like it, almost. There's some differences. I'll tell you what it is here. The P2 over rho plus V2 squared divided by 2 plus GZ2 equal P1 divided by rho plus V1 squared divided by 2 plus GZ1. Now, in Bernoulli's, that was it. Stop. That's Bernoulli's right there. When we derive the energy equation from the system through the Reynolds transport theorem, we get this equation. This term suddenly appears. Okay? Well, this is then similar to Bernoulli. So I'm going to put that over here, I think. And remember what Bernoulli was good for? Steady, incompressible, and inviscid. So neglecting viscosity. Neglecting friction due to viscosity. What we call the inviscid frictionless. Of course, we've derived this thing already for incompressible because we said rho is a constant. Rho is a constant. So we've already said incompressible. We've already said steady. That term went to 0. Well, what's left over here? Oh, the third one. Frictionless. You know what? That term there must be somehow tied into friction. And if we have friction in something, like a turbine or a pump, what happens? Friction eats up the available energy. That's why a pump or a turbine is not 100% efficient. The friction, what does it do? Well, it heats the pump casing, it heats the water inside the pump. Is that useful energy? No, I don't want that. The bearings on your wheel in your car, and the engine, drive shaft, heat up due to friction. What does that do? That takes power away from your engine to drive the car. Do you want that? No. So what do we call this thing here then? We call that the loss of energy. That's the loss of energy due to friction. Okay, so this guy here is called the loss of energy. So comparing to Bernoulli's, this U out minus U in minus Q net in is equal to 0. Okay? Compared to Bernoulli. If there is friction, this is the difference now. If there is friction, then it's not 0. U out minus U in minus Q net in is greater than 0. And that's tied into the second law of thermal. When we derived this thing, we said this is called the first law of thermal, or the energy equation. We get to this point here, we say, you know what, this term always has to be greater than 0. Losses due to friction always use up energy, use up available energy. The loss always has to be a positive term. This thing here always has to be greater than 0. A loss doesn't help you. Friction in your car bearings doesn't make the car go faster. Never, 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 never. Why not? Well, I'll tell you right here. Second law of thermal. That's why we know greater than 0. Okay, so we can go ahead and say that this is the energy that leaves, this is the energy that comes in, and this is the energy that's lost due to frictional effects. So we rewrite that guy over there. I'll put it down again at the bottom here. So we have P out over rho plus V out squared over 2 plus GZ out. Now everything with 1, or in, this is in. I'll change to 1 and 2 in just a minute. We get tired of running in and out on these things. In. Okay, and then we have losses. So, this thing right here is called the losses. Right there, that's the losses. And then, once we do that, we say, you know what? Let's bring back in the work term now. Okay, so let me bring back in the work term. I'll just give you a couple words here. This pressure came in because of the work done by pressure forces on the boundary of the system. So where did that work come from? Pressure? We said there's 3 kinds of work: shaft work, friction work, and pressure work. Where's the pressure work in here? Right there and right there. Where's the shaft work? Right there. Where's the frictional effect work? There would be, you don't consider the frictional work on the boundaries, Friction inside, yeah. On the boundaries, no.
Should it be plus losses or minus losses?
This is minus losses, thanks. And I'll tell you why I put plus there. I'd rather write this thing the other way around. You know how it goes. What comes in is first, what goes out is second. So what comes in, now I'll rewrite in a minute, but anyway, when I write it down, that thing's always a plus sign. I'll show you why in a minute. Okay, so let's go back and include shaft work. So now we have
P out, rho, V out squared over 2 GZ out. And now we have our end terms. And that's equal to W shaft net in minus the losses. Got too many equal signs there. Let's get rid of one of these. This guy up here is equal. This guy is plus right here. There we go. Yeah. Well, that's what we end up with. Sometimes it's called the mechanical energy equation. Sometimes it's called the extended Bernoulli equation. Because it includes now losses and work, that's why it's called the extended Bernoulli's. And now, once we've got that basic equation, now we start to look at different forms of it. Okay, so let's take a look at the first form. By the way, just so you know, where you see a little w, there's a big W, there's a big Q, or there's a little q. They're different, of course. They're different. You see what you do to get little q. You take q dot divided by m dot. To get little w, and make sure you use your lowercase w and a capital W. Little w is equal to w dot net in divided by m dot. You divide them by m dot to get the little lowercase w and the lowercase q. Okay? Now we're going to divide that equation there by g. This is this. Divide that guy by g. HS. I call that W shaft net in. And it's divided by G. HL is losses divided by G. Well, you got to watch the units. You got to really watch the units, okay? Everything in this equation here, that guy is in meters. That means every term in there better be in meters. That means HS and HL are in meters. Okay. You can check it. This guy up here is power. Newton meters per second or joules per second. That's power. Newton meters per second. Divided by kilograms per second. kilogram. What's Newton meters? Work. What's that thing then over there? Work per mass. Work per mass. What's this guy here? Little w. Okay, little w here. Same units. Newton meters per kilogram. Divided by G, meters per second squared. Okay, take that little w, like the little q, do the same thing. Little w and little q, same thing. Okay, divided by G, meters per second squared. What do I get? Cancel, cancel. Newton second squared per kilogram, you say. What is that thing? That's why we're engineers, okay? That's why we get paid the big bucks, okay? You say, what is a Newton? Here we go, back to basics. What is a Newton? A Newton is a kilogram meter per second squared. Multiplied by what? Second squared. Divide by what? A kilogram. And what do you get? Well, guess what you get. Of course. But nobody's going to tell you that. You're expected to know that. That's why we drill you with units all the time. Units, units, units. I'm telling you right now, this is the easy one. What is a kilogram? 1,000 grams. What's a kilometer? 1,000 meters. What's a centimeter? 10 millimeters. What's a liter? 1,000 cubic centimeters. Everything in SI starts with a 1 times 10 to some power. Everything. Easy to memorize? Of course it is. I've talked about it before. And then how about British gravitational? Barrel, 55 gallons. How many quarts in a gallon? How many pints in a quart? You go on and on. How many feet in a mile? How many square feet in an acre? Oh my gosh, nothing starts with a 1. Nothing starts with a 1. What do you want to work in? Of course you want to work in SI. Bad news, not in this country. Some places, oh yeah, some places, it's getting there, but really, really slowly. A gallon of milk, but a liter of soda, right? We're getting there, but it's slow. So anyway, what I'm telling you is, when you're doing homework or exam, you better pay attention to units because they will kill you. They will kill you. And you better know how to do stuff. I say, what in the world's a Newton second squared per kilogram? I must have made a mistake somewhere. Oh no, you didn't. It's perfectly right. Yeah, it's important. Don't downplay it. And that's the easy one. That's the easy one. You know, try and go to G sub C in English engineering. Go to G. Use pounds mass and pounds force. Oh, wow. Now we'll separate the knows from the don't knows. When do I divide by 32.2? When do I multiply by 32.2? You better know that, or it can get embarrassing. I guarantee you that. It can get downright embarrassing. Okay, back to here again. Here we are up here. Everything is in meters now. Isn't that nice? So is Bernoulli in meters. That was a nice form of Bernoulli's. Okay, so we end up with, let's put down with W dot. If we've got a pump now this guy up here means shaft, okay? That's this guy right here. Okay, let's do a pump first, for a pump. Because pretty much in our class, in these energy equations, we probably will have a pump or a turbine, or at least the possibility of that in a problem. So for a pump, W dot pump is equal to gamma Q HP. For a turbine, we have W dot T, T for turbine, P for pump, gamma Q HT. Okay, try it again. I'll do the SI. Gamma. Anytime you see gamma, it's newtons. You see rho, it's kilograms. Newtons per cubic meter. Cubic meters per second. HT, it's all these H's are in meters. Oh, guess what we've got here? Newton meters per second. Guess what that is? A joule per second. Guess what that is? A watt. 1 Newton meter equal 1 joule. 1 joule per second equal 1 watt. Oh, 1 everywhere. Wonderful system. Now go to English engineering. Well, you better know how to convert to horsepower because this world revolves on horsepower. Go buy a pool pump or spa pump. Horsepower, most pumps are specified in that. Their power rating, horsepower. Okay, anyway, these guys now are all going to be in watts. Okay, I'll erase that right now. Okay. And then the efficiency of the pump. We'll talk about pump efficiency. Pump efficiency, the power, it's the gamma Q HP divided by the power into the pump. It always takes more power in than comes out. This is the power that comes out from the power into the pump. Yeah, right. So if you're driving a pump, the pump starts to get warm, the water in it starts to get warm. There are losses due to friction. So turbine, different. For the turbine, we have W dot turbine. That's the out divided by the gamma Q H turbine. That's what you put in. This is what comes out. It's always less than 1. This is what comes out. That's what you put in. It's always less than 1. The efficiency is always less than 1. Okay, and now I'm going to write the 3. Well, there's different equations you can write when you do the energy equations. So remember Bernoulli's? We had 3 Bernoulli's back in chapter 3. I put on the board 3 forms of the same equation, the Bernoulli equation. Here are 3 forms of the energy equation. Okay, the first form. This was on the board a while ago. We're going to use one now. Yeah, this is what I want to do. We're now going to use subscripts 1 and 2, not in and out. Here's a second form. And finally, the third form. Okay, so the first equation, the units of all the terms should be Newton meters per second. That's joules per second, that's watts. Everything's in watts. The second one, we divide it by mass. We divide it by the m dot. Everything now is in Newton meters per kilogram, which means work per kilogram of fluid flowing. Or if you'd rather think about it, divide both numerator and denominator by time, Newton meters per second divided by kilograms per second. This then becomes power per mass flow rate. Or you use this one, where now everything is in meters or feet. This is called the head loss in feet. The turbine, the pump. If there's no pump, HP goes to 0. If there's no turbine, HT goes to 0. If there's no losses, HL goes to 0. Yeah.
Will those m dots always be the same value?
In chapter 5, what we're doing, yeah. It can get, it doesn't have to be, but normally what comes in goes out. Take a pump, of course, what goes in goes out. A turbine, what goes in goes out, of course. Sometimes, no. You can have mixing chambers. Two things go in, they mix together, one thing goes out. Uh-oh, change it now. How do you change it? What did we do? We went around the control surface, didn't we? Go around the control surface. There might be other terms in there, yeah. Okay, so now the bottom line is, I know that's bottom. The bottom line is you're probably going to choose one of these three to work most of the problems on energy in chapter 5. Okay, and we'll work different forms. We'll probably mostly use the last one, just like in Bernoulli. We mostly used the last one. It was kind of convenient and simple. Everything is in meters or feet. That makes life a little bit easier when you can do it than normally you do it that way. Okay, so I'm going to just do one problem today, and then we're going to do the next class meeting. We're going to spend that day going through a lot of those problems in energy, and maybe even start in chapter 6. And by the end of next Monday's lecture, that'll be the end of what you're responsible for the next exam, which is a week from next Monday. That gives you a week to study up for the exam after we finish and say stop here. Okay, that's our plan. Anyway, let's see your homework. You've got 102 and 105. I'm going to work 103. You have 102 and 105 for homework. I'm going to work 103. All right, there's a picture in the textbook on this one. We don't need this anymore. All right, here's an inclined pipe. Go right here and here. There's a manometer here. It's a piezometric tube. Comes out and goes up. There's a piezometric tube here. Goes out, goes up. It's a clear tube. This is a review of chapter 2. We use piezometric tubes to measure static pressure. If we can. Sometimes you can't do it, but if you can. We've got several of those in the fluids hydraulics lab. Several of them in the fluids hydraulics lab. Okay. The left-hand one, let me see if I got this thing right. And by the way, there's, again, a ton of worked examples in your textbook, so take advantage of the textbook and look at those examples, especially when you're studying for the midterm, because they really help. Okay, there it is. Okay, so going from that left-hand point to the right-hand point, we have 1.5 meters. Okay. So from here to here is 1.5 meters. Now let's see where our manometer levels are. What's the fluid, first of all? 103. The fluid, it doesn't say what the fluid is on that page, okay. So then we've got, there it is, 1 meter and 3 meters. So the 3 meters is up high, you got one, so 3 meters. 1 meter and 3 meter. 1 meter here, 3 meters here. Atmosphere. This is 1 meter. This is 3 meters. Okay, incompressible liquid. We don't know what it is. Water, oil, whatever, we don't know. Flows along the pipe. Determine, oh, let's see. I don't know if we need that. 0.75 meter diameter. Pipe or part B. I think I did part B. It's okay. Determine the direction of flow. So our question is it going down the pipe or is it going up the pipe? That's what it has to find, the direction of flow. Okay. Let's see which one I should take. As I said, normally use this guy, so I'll start with him. That's fine. Now you have to assume 0.1 somewhere. So my assumption is the flow goes from 0.1 to 2, and here's 0.1, and here's 0.2. So I'm going to see if that's right. Am I right? Okay, so P1 over gamma plus V1 squared over 2G plus Z1. No pump, HP is 0. No turbine, HT is 0. P2 over gamma plus V2 squared over 2G plus Z2 plus losses. What are losses? Yeah. Matter of fact, he says, what's the head loss over 6 feet of pipe? So the distance from 1 to 2 is 6 feet, 6 meters, pardon me. Yeah, so there's losses. He tells us there's losses. Now, we're really doing this for our control volume. We derive this thing for our control volume. So if you want, you could draw the dashed lines around your control volume and call it the control surface. But it's not nearly as critical here as it is on momentum. There, you've got to draw the control volume control surface. Here, it's like a modified Bernoulli equation of sorts. We write it from point 1 to point 2. That's why it's called modified Bernoulli. But if you want to be official and do it by control volume, and a control surface, which you probably would for a pump or a turbine, then it's still applicable. There's a point 1 and point 2. Okay. P1 over gamma minus P2 over gamma plus V1 squared over 2G minus V2 squared over 2G plus Z1 minus Z2 equal losses. First of all, V1 equal V2. Okay, so why? Let's see, momentum equation? No, of course not. Momentum's for forces. Continuity? Oh, of course it is. Steady state? Yeah. Incompressible? Yeah. Continuity? M dot 1 equal M dot 2. What's M dot? Rho 1, Q1 equal rho 2, Q2. But the rows are equal. Cancel them out. Q1 equal Q2. What's Q? A1, B1 equal A2, V2. A1, though, is equal to A2. Conclusion? B1 equal V2. Got it. Z1 minus Z2. Z1's down here minus my Z2. Okay, so that's 1.5. I'll just cross those guys out there. Okay, let's see, oops, there it's right there. So my Z1 minus Z2 minus 1.5. Okay, P1 over gamma, P1 here over gamma. Now remember how we get P1 from chapter 2. We did this in chapter 2, okay. P1 is equal to gamma of the fluid times the height from where you are to the free surface. 3. Okay, so that guy is 3, so take 3 gamma divided by gamma, and you get 3 minus P2. P2 is gamma times 1. 1 times gamma. 1 times gamma. Divide by gamma. 1 minus 1. 3 minus 2.5. Okay, the losses have to be positive. They can never be negative. If you want to go the other way, go ahead and try it. Start up here and go down, call this point up here 1, call this point down here 2. Use the same equation, and you'll find out that this number is negative. It says impossible, losses can't be negative. Friction never does create more energy. Friction dissipates energy. That's why the second law of thermal has to be held up. Yeah.
Was P1 given to you, or was that derived?
No, it's from the picture.
Okay.
P1 is gamma of the fluid in the pipe times the distance from the pipe center line to the top of the fluid, right there. How far is that? 1. Okay, now just so we know, over here, that's why I like to write this equation this way. With the 1 on the left side and 2 on the right, because this is the energy that comes in with the fluid. The energy that comes in with the fluid. This is the energy added to the fluid from the pump. The pump adds energy to the fluid. This is the energy that the fluid has. This is where the energy goes. It goes out at location 2. It can drive a turbine to create power, and it has to overcome losses. So this is the available energy, these first 3 terms. It's used up. It's used up. Some of it leaves. Some of it maybe a turbine. And the rest of it, losses by friction. So it's easy to think that way. The losses are unavailable energy. You run your car, it gets hot. It powers the car. You know. Can you now use that heat from the engine getting warm and the hood getting warm to drive your car? No, gosh, no. It's lost. It's lost. Don't try and, you say, well, yeah, no, I could put that back in the cylinder heads. No, you can't. It's lost to what? The atmosphere, the air around the engine and the hood and the car. It's lost. You can't recover it. So that's why this is called the available energy. This is the lost energy. L stands for loss. Okay, so we'll come back and we'll work more problems next time on that. But I want to go over a couple other problems that I've had in office hour and also after class. You didn't get it just by the windows over there. All right, let's do problem 5 for it. Okay, water flows out through a thin, closely spaced blades as shown, with a speed around the entire circumference of the outlet. Determine the mass flow rate through the inlet pipe. Looks like this. fluid comes in here and it comes out here. I'll look down on from above now. Looking down on from above. We have the picture given to you in the textbook shows this. And the angle here that goes out is 60 degrees. That's the velocity. It gives you that 10 feet per second. Go back to continuity equation in chapter 5. It's in your notes up on the board. Okay, rho AV. Rho AV is m dot. So if I want to know how much mass flow rate comes out of this thing, I do that. There's my picture. My control volume is inside here. Where's my area vector? Take the dot product. B times A times cosine 60 is, continuity says, steady state m dot in equal m dot out. You're supposed to solve for m dot in. That's what you do, okay? Oh, by the way, remember now, the area vector always points outward from the control surface, control volume, it does. What is that area? Well, I'll make it like this. There's the area the fluid comes out. What is this area? Circumference times W. So that's the area, 2 pi r times the W dimension of that. Okay, so just so you know how to probably do it officially the correct way, use the dot product. Okay, see, that's that one. Oh, and by the way, the second problem, just so you know, that's this container with water coming in, and there's water in here, and there's gasoline up here. Gasoline, when the water comes in, it pushes the gasoline out. I think they give you the water in, they want to know how much, 100 liters per second, something like that coming in. They want to know how much gasoline goes out. Well, you know, if I push a gallon of water in here, guess what's going to happen? A gallon of gasoline goes out here. That's the equation you need. That's the only equation you need. M dot gasoline equal m dot water. And the water, they gave you Q. Rho times Q. Okay. Rho of water times Q, okay. And that's the change of the weight of gasoline in the tank. That's the weight of change of the gasoline. This is gasoline, by the way. Q of water. It's kind of mixed, you know. Q of water. Q of gasoline. Okay. Okay, so that's the kind of the easier way out of that problem. Just to realize that if you push a gallon of water in the bottom, a gallon of gasoline is going to come out the top. All right, now let's take the last few minutes, and you have problem 412 for homework, and I've had 2 or 3 people come in the office hour wanting to know.
Professor?
Yes.
So, my question on 512 is that by conservation or the continuity for it to be steady state, m dot gasoline and m dot water, that since they have different densities, you'll have a larger volume.
Yeah. this is a Q, pardon me, thanks. Thanks. Q water. Now, once you get Q water, once you get Q gasoline, I'll do it officially. Okay, now I've got Q gas. Now I put Q gas down here, multiply it by rho gas, now I get into that gas, yeah. That's
Okay, all right.
Thanks. Okay, 412. It's a thinking problem. Boy, you've got to really think. I did one in class, a real simple one. I said, I'll do a simple one in class and let the hard one, you try it. All right, I'm going to do an intermediate one now. Harder than I did in class, but simpler than what I got assigned to homework. Very similar though. All right, here we go again. One more time. This is problem 412 modified. All right, smoke plume. Lasts for 5 hours. Smoke comes out of a smokestack for 5 hours. I'm going to put several graphs on the board, so we need some space. All right, there are 3 different segments. First, for the time 0 t to 3 hours. The wind speed is, in vector terms, 10I minus 5j. Plot where the plume is. Show the streak line of the plume at 3 hours. Okay. The origin. And by the way, the plume for 3 hours, it's emitted at 0, 0. Yours was emitted at, I don't know, minus something and plus something. That's okay. All right, here's 0, 0. 5, 10, 15, 20, 25, 30, okay, that's probably fine. 10, 20, 30. Let's see here. 5, 10, 15, 20. 5, 10, 15, 20. All right, the first bit of smoke that comes out of the smokestack, when it comes out, it has that velocity. It goes to the right and it goes down. Okay, got it. After 3 hours, where is that first bit of smoke that came out? The first bit of smoke emitted after 3 hours. Velocity in the x direction, 10 miles per hour. This one, 5 miles per hour. After 3 hours, 3 times 10, 30 miles. Okay. 10? Yeah, 30 miles, okay. I guess I get this in. That's okay. No, that's way too big. Sorry about that. I'll be out the window with this if I do that. Make this 20, 40, 60, 10, 30, 50. I'll leave that. Okay, that's fine. All right, after 3 hours, 10 times 3, 30. 30 miles it went. Which way? Due east, 30 miles here. But it also had a southeast direction to the plume. The plume is blowing to the southeast. It went down 5 south, 5 miles per hour times 3. 15 down. 30 to the right, 15 down. There is the first bit of smoke that left the chimney at time equals 0, after 3 hours. Where's the smoke that left the chimney at 3 hours? Right here. Connect the dots. There's the streak line of the plume after 3 hours. Okay. I'll erase this. For time 3 to 5 hours. Now the wind speed changes. Now it's 15 miles an hour I, that's X direction, plus 10 miles an hour in the J direction. Show the streak line at T equal 5 hours. All right, 5, 10, 15, 20. Okay, let's see, this one I want to go out to maybe 80. 10, 20, 30, 40, 50, 60, 70, pretty close, 80. First of all, where did this line of smoke go? Well, at time equal 3 hours, it was here. Then the wind changed. For how long? Looking at? From 3 hours to 5 hours. What's the difference in time? 2 hours. Take the smoke particle right here. In 2 hours times 15 miles an hour, it went 30 miles due east. 30 miles due east. He's sitting on 30 right now. He went to 30. He's out there now at 60. How about the Y direction? He went north 10 miles an hour times how many hours? 2 hours. 2 hours, because 3 to 5. 2 hours. 20. Which way? North. 20. North. Where did he start? 15. Where is he now? Up here. Where is that? That's at 5. He's really right there. Just so you know where he is. Okay, so over here. And by the way, where did this guy here go? He started at 0. In 2 hours, he went 30 up, 30 to the right, 20 up. 30 to the right, 20 up. 30, 20. He's right here. This guy went up here. This guy went over here. These are molecules of smoke. So here he is. That line, if I had it drawn right, it should be the same slope if my slope was correct. It moved up here. This line moved up here. But no, wait, there's still smoke coming out after 3 hours. It goes for 5 hours. Okay, we sit up there, 5 hours, smoke down the stack. Okay, well, when the smoke came out of the stack at 3 hours and 1 second, 3 hours and 1 second, which way did it go? 15 miles an hour, times how long? 2 hours. 30. 2 hours times 10, 20. It went to 30 and 20. 30 and 20. Oh, he's sitting right there now, right next to him, his buddy right there. That smoke left at 3 hours and 1 second. How about the one that left after 3 hours and 30 seconds? He's here. 3 hours. 3 hours, 34. 3.5 hours there. 4.5 hours there. 5. The last guy comes out. Last guy that comes out, he's right here. Back over here, I can't know if this thing drawn right. So 60 up to 5 here. Okay, now he goes at 20 and 30, so here's 30, and there's 20, he's up here. And this amount is right there. There's the whole smoke. 5 hours, 5 hours. Smoke went out that way for a while. It went southeast. Then the wind shifted, and it went up that way, and the smoke leaving here from 3 to 5 went straight out that way, northeast. North, that's north, that's east. Okay, out to 10. For 5 to 10 hours. V is equal to 5I. The wind's dying down. It's 5 miles an hour east now. 5 miles an hour east. Show streak line. At 10 hours. Okay, here we go again. 5, 10, 15, 20. 5, 10, 15, 20. And over here, let's see, 10, 20, 30, 40, 50, 60, 70, 80. Okay, take the one at 0, just make life easy on ourselves. Take the one at 0, that's the last smoke part came out. This was the last smoke particle that came out of the chimney. At when? 5 hours. For the next 5 hours, what did he do? He drifted east at 5 miles an hour. Times how long? 5 hours. 5 times 5? 25 miles. He went due east. 25 miles. He's out here now at 85. So there he is right there. That's the point. That was right there. He moved out to here, okay? And then, let's see, okay, up there. Let's see, this guy, oh, I guess I'm out of proportion here. Yeah, I'm out of proportion here, okay. Because, oh, wait, okay, I'm sorry, 25, where am I going? 25, excuse me. He moved 25, I'm going from 60. He moved 25, he's out here. Let's take this guy out here now, he's at 60. He's gonna go due east, 5 miles an hour, times 5 hours, 25, 60, 70, 85. 85. Did he go anywhere in the Y direction? No, he didn't. Where was he here? 5. Where is he here? 5. Pin the two endpoints down first. Left-hand side, right-hand side. Where did this guy go up here? He was at 20 and 30, 20 and 30. He moved due east 5 miles an hour times 5 hours, 25 miles from where he was. He was at 30 plus 25, 55. There he is. Once you got those three guys pinned down, now it's simple. Connect the dots. There it is, the streak line after 10 hours. Oh, big, long explanation, but people want to know how to do these things, so I thought I'd spend some fast time on it. That's how you do them, okay? Yeah.
So for each separate wind velocity, you have to make a separate graph?
You don't have to, but life is simpler if you do.
Okay.
You can work at ME214 problem in statics and try and do everything on one sketch. And I guarantee you, you will suffer sometime in your life doing that. It's always better to draw more diagrams. That's why I did it this way. You're trying to do it on one, like let's say the solution does it. Oh no, you're asking for confusion, mass confusion. Try and put these three guys on this thing over here. My gosh, you're asking for confusion. You simplify something if you spread it out and do a graph for each particular time interval. Yeah, at the end of the time interval.
So you plugged in the initial, which is 5, into the equation, and then you got 25.
I plugged in, no. I plugged in the differential time. How many hours between these two?
5.
Times what? You got it. 25 miles, every point goes 25 miles to the right. Every point on this line and this line go 25 miles to the right. I made it a little bit easier than the problem he did for the assigned problem, but if you can understand this and do it this way, you'll get that problem fine, I guarantee you. Okay, good stopping point, so we'll see you on Monday. Homework is due on Monday.